In this lesson, we're going to go through Bayes' theorem. But first, let's start by defining what a partition of the universe is. Now, if we are given the universe U of a certain random experiment, and if we define n events, B1 till Bn, that form a partition of U. Now, what does it mean that these n events form a partition of the universe U? Now, if we before we go through the conditions of these n events forming a partition of U, let's just go through the diagram. Now, as you can see in this diagram, I have included 6 events that form a complete partition of the universe U. You can see that the events are totally disjoint. Disjoint means that they don't intersect. B1 cannot intersect with B2 or B3, etc. So these events cannot intersect 2 by 2. And at the same time, their union form the whole universe. B1 union B2 all the way to union B6 is equal to U. And a third condition for these 6 events to actually be a partition of the universe is that none of them have to be empty. Has to be empty. Okay, so these are mainly our 3 conditions for n events to form a partition of the universe U. So each event in this partition should not be empty. They should not intersect 2 by 2, and at the same time their union should be the whole universe. Now, if we move to the formula of total probability, which comes from the partition of the universe. Now, we have here the same diagram, including the 6 events that I included in the diagram that form a partition of the universe U. Now, if we are given another event of the same random experiment, whose U is its universe. So we can see here on the diagram, I have included event A. So A should intersect at least one of the events forming the partition of the universe. It doesn't have to intersect all of them, as the case in the diagram I have drawn, but in fact, it has to intersect at least one. A could be a subset of one of the B's forming the partition of the universe. It's not really a crucial condition for A to intersect all of them. Okay, but however, now, as you can see here, A intersecting at least one of the events forming the partition of U. So A, we have here A inter B1, we have here A inter B2, we have A inter B3, etc. So we have an intersection of A with at least one of the events forming the partition. So according to the formula of total probability, that the probability of A is the sum of the probabilities of the intersection of A with each of the events in the partition of U. Now, even if A inter B1 is empty, its probability is 0, so it will not affect the sum. So this is the formula of total probability. The probability of A is the probability of A inter B1 plus the probability of A inter B2 plus all the way to the probability of A inter Bn. Now, if we can see this through this quick example, we have an urn containing 9 balls. 3 of them are yellow, numbered 1, 2, 3. 2 of them are blue, numbered 1 and 2, and 4 of them are green, numbered 1, 2, 3, and 4. Now, we decide to draw a ball at random. We consider the following events. We have Y, the event of the ball drawn being yellow, B, the event of the ball drawn being blue, G for the ball drawn being green, and we have another event A, which is the ball drawn holds an odd number. Now, if we were to represent this in a quick Venn diagram to actually see that Y, B, and G form a partition of the universe, since it's one of the possible partitions, in fact, and we will talk about this later. So if we look at the universe U, which is the urn that contains all the balls. Now, we only have three colors. We only have yellow, blue, and green. So yellow, blue, and green form a partition of the universe. And I have highlighted here in red event A, which says that, or consists of, the ball drawn being odd. So we have for the yellow balls, we have three balls numbered 1, 2, 3. For the blue, we have 1 and 2. And for the green, we have 1, 2, 3, 4. Okay, so for the yellow balls, how many of them hold an odd number? In other words, what's the intersection of A and Y? It's 1 and 3. What's the intersection of A and B? It's 1. What's the intersection of A and G? It's the set 1 and 3. So according to the formula of total probability, the probability of A is the probability of A inter Y plus the probability of A inter B plus the probability of A inter G. Now, what about A inter Y? Now, ask yourself, in my urn, how many yellow balls hold an odd number? I have only 2 yellow balls holding an odd number, and that's 2 out of 9. Similarly, for the blue balls, how many blue balls hold an odd number? It's 1 out of 9. We're speaking of the whole urn here. So, in fact, and the same thing for A inter G. So the probability of A is 2 out of 9 plus 1 out of 9 plus 2 out of 9 again, which in total gives me 5 out of 9. So usually if I were not to give you the partition of the universe, if I only gave you the urn and asked you for the probability of drawing an odd number, you'd immediately count the odd numbers and divide them by the total, which is 5 out of 9. Okay, so basically, this is another way to show you that you usually, without knowing it, use the formula of total probability and consequently Bayes' theorem that follows. So if we were to move to Bayes' theorem, if we were to generalize it, now I'm going to illustrate it on a tree diagram because it's the easier to show. So if we have an event B and its complementary event or its opposite event B prime, and we have a probability of B and the probability of B prime. Now, realizing A given B and realizing A prime given B, don't forget that these branches here of the tree diagram are the conditional probabilities, because for example here, as we've already mentioned before, because over here B is realized, and here we're finding the probability of realizing A knowing that B is realized. So these are the conditional probabilities. So having this tree diagram, you'd know that to find the probabilities of the intersections, we just multiply the probability of B with the probabilities of the conditional probabilities, in addition to P of B prime with the probabilities of the conditional probabilities to find the probabilities of these intersections. Okay, so according to Bayes' theorem, if I wish to find the probability of B given A, the tree diagram gives me probability of A given B. B is realized. Now, if I wish to find the probability of realizing B given that A is realized, now, according to the formula of conditional probability, we know that probability of B given A is the probability of A inter B divided by the probability of A. Now, according to the tree diagram, the probability of A inter B is probability of A given B times the probability of B. You just multiply them to find the probability of their intersection. Well, to find the probability of A, now there are two possible ways to realize A. We could realize A after realizing B, and we can realize A after realizing B prime. So in fact here, this is the formula of total probability that you can see at the bottom here at the denominator. because B and B prime form a partition of the universe. B and B prime are both not empty. They do not intersect, and their union forms the universe. So B and B prime being a partition of the universe, then the probability of A is the probability of A inter B plus the probability of A inter B prime, which you can see here at the denominator in terms of the conditional probabilities. Now, in this last example, we're going to see how quick and easy this is. If you were to just do it on the tree diagram, you'd be able to pick up Bayes' theorem immediately. So if we have in a university 65% of females and 35% of male students, 25% of the females take statistics, while 60% of the male students take statistics. Now, a student that takes statistics is selected randomly. Find the probability that the student is a female. So as you can see here, that taking statistics is an event that is realized. So the probability that that student is a female is in fact the probability that it's the female given that it takes statistics. So that's the probability that we need to find. Let's just first illustrate this problem on a tree diagram. So we first have the university that is split into female and male. So female and male form a partition of the universe, representing the university in this case. So we have 0.65, the probability of choosing a female, and we have 0.35, the probability of choosing a male. Now, when we say 25% of the females are taking statistics, it means that selecting a female is a realized event. So the 25% or the 0.25 is the probability of taking statistics given that it's a female. And similarly, if this is to be 0.25, this is 0.75, of course, the probability of being a female, the probability of a female not taking statistics. And similarly, we have 60% of the male students take the course. So this is the conditional probability of taking the statistics course given that it's a male. So we have here choosing a male is an event that is realized in this case. So that's the 0.6 here, which leaves me for 0.4 here for S prime, for the opposite event of taking the statistics course. So as we've already mentioned, now the student that we choose at random is a student that takes statistics. So that's a realized event. Okay, so to find the probability that that student is a female, that's the probability of choosing a female given that it takes statistics. So according to the conditional probability, that's the probability of F inter S divided by P of S. Now, according to the tree diagram, the probability of F inter S is what we can find here by considering 0.65 times 0.25. While for the probability of S, since the females and males form a partition of the universe, then the probability of taking statistics of a student chosen to take statistics, that's the probability of F inter S plus the probability of M inter S, which you usually do intuitively through on the tree diagram or through the tree diagram. So if we were to just fill in the numerator and denominator, as we've already seen, as we've already mentioned, that the probability of being a female and take statistics, that's 0.65 times 0.25, and at the denominator, it's the probability of S, which you can find here. There are two ways to realize S. We can realize S by choosing a female, and we can realize S by choosing a male. So it's F inter S plus M inter S, which you can find by multiplying them and adding them at the denominator. And finally, this leaves us with a probability of 0.436.